Hello, I think welcome. This will be the first in a series of lectures on physics. And my goal is really to give you an intuitive feeling of what physics is all about, because especially on the mechanics side of things, projectile motion and force and moments, it's actually pretty intuitive. So, well, let me know if I'm not giving you an intuitive sense. Let's just start with probably the most basic formula in physics, and a lot of y'all have already seen this. Is distance is equal to velocity times time. And you might have seen it in different forms. You might have seen it written as distance is equal to rate times time, or distance is equal to speed times time, or instead of a d, if you're doing it in math class, sometimes they'll write an s for distance because they use d for derivatives. But it's all the same thing. It just says the distance you travel is equal to the speed or the velocity you travel times time. Now, before I do a couple of quick just example problems just to hit this point home, I just want to make a slight distinction between velocity and speed. So, when people use it in everyday language, it tends to be used interchangeably. It's kind of how fast are you going, right? Velocity versus speed. But technically, there's a difference. Velocity is a vector measurement, and speed is a scalar. And I probably have already confused you. And all you have to know is a vector has a magnitude and a direction, right? So if I were to give a velocity, I really shouldn't just say 5 miles per hour. I should say 5 miles per hour north. Or instead of saying 5 miles per hour north, I could say negative 5 miles per hour south, right? Those would be the same thing. While speed, or a scalar, only has magnitude. So speed would say 5 miles per hour, but I don't know what direction I'm going in. I could be going forward, backward, left, right, north, south, up, down, who knows? So that's the technical difference between between a vector and a scalar, and between velocity and speed. And it might not seem so obvious, and probably on these few example problems we're doing right now, the distinction probably could be used interchangeably. But later on, as we progress to fancier problems, I think you'll see that velocity is a more useful notion, because you have there's the idea of a negative velocity, right? You can go in one direction, which is positive, and then you could turn around and go negative. And with speed, there's no direction involved. So with that said, I don't want to dwell on that too much, because I don't want to make you think that this is difficult. Let's do a couple of really quick problems. I mean, if I were to go, let's say I went 50 meters. So 50 meters, so distance is equal to 50 meters. So I go 50 meters, and time is equal to, and this should really be, well, I guess you could say distance, or you could say actually change in distance, but for the problems we'll do, it doesn't make a difference. Let's say the time is, and once again, this could be change in time as well. The time is 10 seconds. 10 seconds. So if we use that formula, we have 50 meters is equal to velocity times 10 seconds. So this is a pretty simple algebra equation. If we want to solve for velocity, we just divide both sides of this equation by 10 seconds. And I'm doing this because I actually want to show you that when you divide the numbers, you should also divide the units with them, and then you'll always end up with the right units. So let's multiply both sides of this equation by 1 over 10 seconds. So then I get 1 over 10 seconds times 50 meters is equal to velocity times, well, I'll write it all out. Later on, I'll skip some steps. Right, this obviously cancels out. That's why we did it in the first place. And then the 50 and the 10 cancel, and this becomes 5. So we're left with 5 a meter in the numerator and a seconds in the denominator. I could write it as sec, or just with an s. So 5 meters per second is our velocity. You could have done that, but the one thing I just wanted to highlight is that the units you can manipulate with the numbers, and then you always get the right answer. And it might have been obvious in this case, you didn't have to do it this way, but once again, later on when we start doing power and work and energy, which is actually the same thing as work, but once we start doing those things, then the units might not seem so obvious. So it's good to be able to deal with the units this way. So, and we could solve. If I said that the velocity is equal to 7 meters per second, and that time is equal to, I don't know, 5 seconds, how far did I go? Well, I could use that formula again. Distance is equal to velocity, 7 meters per second, times time, which is 5 seconds. And once again, not only can we multiply the numbers, 7 times 5 is 35, but we can multiply the units. So we have meters over second times seconds. You can almost treat them like variables, but they're not. They're units. So meters over seconds times seconds, well then a second in the numerator and a second in the denominator cancel out. So you're left with 35 meters. And there, not only do you have the right number, you have the right units. And actually, this is going to be super useful when you have, if you have to convert from centimeters to meters, and hours to seconds and all of that. And maybe we'll do a couple of examples. Actually, a while ago, I actually already made a separate video on unit conversion, and that's going to come in really handy when we do the physics. With that out of the way, let's make things a little bit more complicated. Image. So most of what you've probably experienced so far, distance is equal to velocity times time, or rate times time, is where velocity is constant, right? Where you're going 30 meters per second, you're always going to 30 meters per second, and you'll stay going 30 meters per second. But we know from moving in life, moving generally, that your velocity isn't. I mean, sometimes you're stationary, and then sometimes you're moving, and in order to start stationary and then get moving, your velocity had to change, right? So how could we describe a change in velocity? And once again, I don't think I'm teaching you anything fundamentally new. You know what it is. It's acceleration. So velocity is acceleration times time. And there's a pretty good analogy here, right? Just as distance is velocity times time, velocity is acceleration times time, or you could view it as the change in distance over the change in time is velocity, while the change in velocity versus the change in time is equal to acceleration. Oh, my phone's ringing. Let me answer that a little bit later, because once again, you are more important. So where was I? Oh, okay. Oh, I was saying how they're very similar, right? At least there's kind of an analogy here. So what can we do with this notion? Well, I'm going to do a bunch of what I think you'll find is pretty useful. They're called projectile problems, and projectile problems involve the acceleration of gravity. And but we could do other acceleration problems, involving an acceleration of car, et cetera, et cetera. And actually, I probably will do that. But the acceleration of gravity is, well, it's actually 9.8 meters per second, again downwards. And once again, acceleration is it's actually not down, it's towards the center of the Earth. Acceleration is also a vector quantity. But for the sake of our computations, we'll just say 10 meters per second. So acceleration is equal to g. G is normally the variable used when people talk about the acceleration of gravity. And let's say that equals 10 meters per second squared. I know what you're thinking. This is kind of a strange set of units. Meters per second squared. It's hard to visualize. Well, that's acceleration, and I think once you see it used in some of these formulas, it'll start to make a little sense in terms of how these units work out. So let's start with a fairly simple problem. Let's say I drop a rock from, and I don't recommend you to do this, you could kill somebody. Let's say I drop, not a rock, a penny from the Empire State Building, and I'm assuming no air resistance. And actually, I just looked at the clock and I realized that I'm running out of time. So I'm going to actually start this problem in the next presentation. I'll see you soon.